Hi, this is Guillermo Escribano, and I'm currently on my fourth year as a PhD student here at UC3M. My thesis is being carried out in collaboration with GMB and the European Space Agency on the topic of maneuver detection applied to space surveillance and tracking. Some of you may be wondering why is space surveillance and tracking needed in the first place? Well, here you can see a chart on the number of big enough or trackable objects in Earth orbit, which is increasing at a fast pace. In order to keep up with this growth while maintaining accurate space object catalogs, different organizations have set up global sensor networks. Here you can see the one being currently operated by the European Consortium, EUSST, and their end goal is to keep track of Earth orbiting objects in order to maintain the integrity of the orbital environment, mainly by avoiding collisions. So why do we care about maneuvering satellites then? Uh, well, let us consider a situation in which some target performs an unknown maneuver. We can predict its future state following natural orbital dynamics, but obviously this does not provide a good estimate. At some point, we receive an observation, and we need to find out whether it corresponds to this satellite, and if so, provide some state estimate. This estimate is going to be used to compute the probability of this satellite colliding with any other object in our space catalog, composed of all the objects we can accurately track. Uh, One of the solutions proposed in the literature relies on the use of statistical distances, for instance, in the measurement space. Though this can be applied to small maneuvers, it does not consider dynamics of any type and typically assumes Gaussianity is preserved in the state and measurement spaces. Still, one can provide a state estimate by solving a stochastic optimal control problem, which is subject to the assumption that the transfer is optimal in some sense, like typically we assume fuel optimality. The problem is that if the observation is partial, this is if we're not able to infer the orbital energy and the orbital plane from the measurements, then the estimate will always be biased. In fact, filter consistency cannot be ensured, since there is not a prior distribution from which to infer the posterior, but the posterior is rather derived solely based on the observed probability distribution function. This poses an even greater problem for data association, as it lacks a proper definition of measurement likelihood due to the lack of a prior density. The question is, can we consistently solve the maneuvering target tracking problem in space? Or in other words, can we propose a methodology that allows for proper data association and is not subject to biased estimates? Well, it seems like reachability analysis fits these requirements. In general, and especially true for low thrust satellites, it is not hard to define controllability bounds, for instance, in the thrust magnitude. Then it is possible to use such control bounds to define a set of states that can be reached by some target subject to certain time of flight and initial conditions. So application of this methodology to multi-target filtering is straightforward, since one can already build some prior PDF in the event of a maneuver as uniformly distributed throughout the reachable set. Then one can apply some advanced multi-target filter like the generalized label multi-Bernoulli to carry out data association under uncertainty. We would then be left with an updated multi-object distribution that conveys information brought by a set of measurements. In fact, this class of advanced filters naturally allows for uncertainty regarding the cardinality of the population and the validity of the measurements themselves. This is, it accounts for target birth, death, misdetections, and clutter. And in this case, we also added maneuvers. So let me now briefly comment on the main outcomes of our research. So here we can see the velocity estimation error and covariance bounds when tracking an orbit racing satellite using radar surveillance data. As expected, during maneuver intervals, covariance grows by up to 2 orders of magnitude, since the information content in the measurements is unable to further reduce the dynamical uncertainty. There's some interesting bias that builds up along the tangential velocity component, which is countered by a strong maneuver around day 9. What we can see here is the filter finds some consistent solution with a lower velocity and thus energy and control requirements, and sticks to it until some measurement proves otherwise. This explicits the need to drop the optimal control assumption for limited observability, as it can lead to biases the filter may be unable to recover from. So based on the previous findings, we implemented a multi-target filter with an informative or uniform maneuver priors over a readable set. So in these figures, we provide some measures of the biasness and consistency of our multi-target filter for an optical surveillance scenario with 10 targets, five of which perform 2 random impulsive maneuvers between days 1 and 2. Even if the posterior errors climb up to 40 kilometers, the estimations remain consistent for the majority of the test cases, as indicated by the scale normalized estimation error squared values near 1. So these high deviations stem from the multimodal characteristics of early post-maneuver PDFs, which convert to within usual non-maneuvering figures when enough measurements become available, in this case 2 to 3 days after the maneuver period. So in a nutshell, within this thesis, we have developed some official control distance metrics that can be readily applied to two-body problem reachability. We have then applied this approach to maintain custody of a target in challenging surveillance scenarios. In this case, a low thrust orbit racing maneuver. And finally, we have shown how this approach can help to resolve ambiguity regarding data association by providing consistent maneuver prior distributions. If you're interested in the development of the methodology, you can find a detailed explanation of the different methods in the proceedings of these 5 conferences. There's also a journal article on the combined use of control metric bounded priors and historic data or heuristics, which can help reduce uncertainty when maneuver modes follow certain patterns, as in the case of a geostationary spacecraft, for instance. Last but not least, the methods developed to solve data association in a multi-target setting were carried out in collaboration with Dr. Brandon Jones during a 6-month stay at the University of Texas at Austin. So, well, thank you for your attention. And if you have any questions or are interested in our work, please do not hesitate to contact me.